I'm Squirrel Iserloh. I teach at SMU Guildhall, which is a grad school for video game development, and I've been in games for over 2 decades. I've worked at a bunch of companies as a technical director and a lead programmer. And this is our 18th year, I think, 18th or 19th year having these math and physics talks at GDC. So this is a nice time-honored tradition. Today I want to talk about curves revisited. And my motivations for this are a couple different things. So first, I gave a talk in 2015 in these sessions about basically easing functions, right? Ease in and ease out and smooth step and that sort of thing. And how do you derive them and how do you intuit them and what's the math behind them and how do you invent your own and how do you customize them? And then the last slide of that talk was sort of a tease of me saying, well, there's a whole different set of ways you can derive these and customize them using Bezier and Hermite curves and stuff. So that's kind of what this talk is taking up where that one left off and some other things. So if you know everything there is to know about curves and splines, hopefully there will still be stuff you'll learn today. If you know everything there is to know about easing functions, hopefully there will still be some insights for you today. But that's kind of what we're going to be covering. It's also kind of a love letter to my past self of, gee, I wish someone had told me this stuff, 15, 20 years ago. So that's kind of my target audience in many ways, is me 5 years into development, sort of knowing stuff, but not always completely understanding, sometimes just using my tools like a black box. Another motivation is if you go to, say, Wikipedia, which is fantastic in general, on the subject of splines and Bernstein polynomials, you'll get pages full of Greek letters and stuff like this. And for example, when you read this, do you see Pascal's triangle? No, probably not. Later you'll see it in the talk and it'll be much more obvious. So I think thanks, but no thanks, Wikipedia. I think there are much more intuitive ways of understanding this stuff. So really this is also about me just sort of iterating on this stuff and helping me get a solid, intuitive, fundamental grasp of these things, and then sharing that with you guys. And because it's in the morning, I promise I will go slow and we'll be very gentle with you. So we're going to ease you in with a smooth start. Cubic if you want it. So today the topics include parametrics, interpolation, Bezier curves versus easing functions, curve splitting, Hermite curves, and if we have time, splines. We'll see how far we get into them. And I'm going to go fairly fast. My goal, again, is to sort of plant seeds and unlock things for you to go later and think about and work through on your own. So I'd rather cover a whole lot that you plant a bunch of seeds, 80% of which might land, than take my time. So I'm going to go a little fast. More important than the topics, though, might be the takeaways. First, I want to help increase your intuition for curves and splines, what they are, right? Beyond what Wikipedia offers. Intuiting different algebraic representations and code representations, constructing easing functions like smooth step or any other custom weird thing you want to do from these kinds of curves. Talking about alternate ways of controlling curves and having some curves look like other curves and sort of masquerade as each other. We're often going to want to have splines and curves that we're going to want to slice to make a branch in a game with paths that guys are marching down or something. And there's some interesting stuff with curve splicing. I'm just going to go into the basics of how it works. There's some pretty cool techniques. We'll look at smooth step and smoother step and cubic Bezier in a little depth and ask a question, what happened to smooth step 4? If you don't know what that means, I'll explain. And then we're going to talk a little bit about curve and spline velocities and continuity, again, time permitting. That's sort of the bonus thing on the end, right? As a software engineer, you're supposed to have really conservative goals you know you can hit and then really aggressive stretch goals. So splines are my stretch goal today. So let's start with parametrics. So what I mean by parametrics is some kind of function that you plug in a t, usually just a number like a float, typically from 0 to 1, and you get something out, right? And we often use it from 0 to 1, where 0 is at the start and 1 is at the end. So this might be something that we change that t over time, right? And that's where t, I'm assuming, comes from. So for most of today's talk, you can lerp colors, you can lerp strength and damage curves, you can lerp AI aggression, but we're going to be visualizing stuff geometrically for intuitions. So mostly I'm going to be talking about a function where you plug in t and you get out an x and a y, that kind of thing, or an x, y, and a z, like geometric parametric functions. So for example, this function, if you plug in t, you get out the position t comma 0. So as t increases, obviously that'll be a point that's moving sort of in the positive x direction, right? Proportional to t. That's pretty obvious. If we return t comma t, then if I plug in a 6, I'm going to get 6 comma 6. I plug in a 7, I get 7 comma 7. So we're moving in a diagonal line away from the origin, perhaps. If I start having a little more fun with this, I say, well, the x-axis is just constantly increasing, moving away. But the y-axis is going to be doing this. Then I'm going to be sort of moving away as I wave away from the origin. Cosine comma sine, hopefully, you're familiar with that is, I would say, the number one piece of trig that you have to know. That's the coordinates of a point moving around a circle at an angle t. So I'm going to start with a demo. I actually have a lot of demos here. All right, so this is a simple parametric function where I'm plugging in t comma t, like we said. And so I'm going from 0 to 1. And over that period, I go from the position 0, 0 to 1, 1. That should be obvious to everyone, hopefully. And here's another one where I'm doing something that's a little more wordy, but it's still very simple. I'm just going from the start point to an end point over the course of 0 to 1, right? And I could think of this as two different ways, which we'll look at later. Either I start at the start, and then I'm going to move some percentage of the distance along the path to the end, or I'm just sort of going to mix and crossfade from start to end. And you can see this is a 3D line that's going from start to end point. Here's that other example, though I have it now in x and z instead of x and y, so it's 3D. But it's just moving to the right constantly, and it just happens to be hopping up and down. Up is z in this case. So that's a parametric sine wave. Again, it's parametric because I'm plugging in t and I get out an answer, right? In this case, a position. And here we're having a little more fun. It's moving to the right constantly. That's the x part. The y part is going to be going a lot back and forth. Instead of -1 to 1, the sign will give me -9 to 9, right? Whereas this 9 is going to make that sign be much faster than the other one. So we have sort of a sign on sign thing. So we're talking about parametric equations, and I want to distinguish them from implicit equations. So our classic line equation from junior high is y equals mx plus b, or just y equals x. And that's just true or false, right? 6 comma 6, true, y does equal x. 5 comma 6, false. It's not on the line. So it's a test as to whether something is or is not on the line. Whereas the one on the right is the parametric equation for a line, which says, hey, plug in any t, and I'll give you t comma t, and that generates the same line, in fact, right? But it has a distinctive sort of start and direction, right? If I start at t equals 0 and I start increasing. And likewise, we can compare implicit, the rule for if you're on a circle or not, versus how do you make a circle, going cosine comma sine around. So first quiz question is, how would you write this parametric function? This is a spirally cone thingy shooting off along the x-axis, and it's kind of spiraling around the x-axis as it gets bigger. So my thought process for this is, I want to start with, well, it's going to be going to the right, it's going east. So I know the x will just be sort of t, right? As t increases, x increases. And then I want to make it spiral around, so that smells like cosine comma sine. So I'll put that in the y and z, because that's where we're spinning like a circle. And then lastly, I want the radius of the circle to get bigger and bigger and bigger as it goes. So I'm going to put a t times whatever that is. So as t increases, so does the circle. So that produces a helix cone shooting out from the x-axis. All right, so let's look at interpolation. So starting very simple, we want to average two numbers. We all know how to do that. We can rewrite it, though, to be a 50-50 blend of the two numbers, right? Same thing. I think that's a more useful representation. I would call that half of A and half of B. Of course, we don't have to do 50-50. We can do 70-30 or whatever adds up to 1, right? So this is a 65% B mixed with 35% of A. We can use any blend weights we want, 2 or 3 or however many, as long as they add up to 1, right? So in general, I would say there's some amount of A mixed with some amount of B, right? And S is how much A I want, and T is how much B I want. But really, there's just T, and I'm using S to mean whatever's left over, right? So if T, meaning the B part, is 70%, well, I guess there must be 30% left for A. So that's how we would compute S. And mathematicians would leave the T, the 1 minus T in there, and they do. And when they multiply it all out, it gets big messy. And this is why some of those things on Wikipedia are not as intuitive. By writing it this way, which I never see anybody do, the math becomes faster, more elegant, easier to understand, easier to extend. But anyway, there's one knob T. So we're going to call this LERP, right? We're going to LERP, which stands for linear interpolation, from A to B, where T is sort of the fraction of the journey, or rather it's the weight that B has, right? So there's really 3 ways to write this. And I know this is very, very elementary, but I want to focus on the mentality here, not the math, because we're about to use that mentality. So the first way to think about it is there's some of A mixed with some of B. This is a 60-40 blend, right? The second way is if you don't use S, it's obviously the same math, but now it has a smell of, well, B has a percentage and A gets whatever's left over, right? And again, the same math, just written a different way, but this reads like start at A and then move some fraction of the journey of the displacement from A to B, which is B minus A. All right, so generally we have linear interpolation and nonlinear interpolation. We're going to use both very heavily in all of these easing functions, curves, splines. Okay, so for nonlinear interpolation, generally we'll think of this, our most common example will be easing functions or tweening functions. So we want to go from A to B, but not in a boring way. So here on the right of this graph, we start at 0, we end at 1, but in the middle it's more interesting. It's not just a straight line. This is ease in for artists, quadratic ease in. I call it smooth start 2, right? It starts off smooth. This is smooth start 3, smooth start 4, so we can have a higher order power. And if you're interested in this stuff, that 2015 talk is just tons and tons and tons of fun with easing that you can go check out. Smooth stop, I could, if this is expressed as motion, would be I start off really fast and then I come to a nice smooth stop, right? And I could do that squared, cubed to the 4th power, so I can have more aggressive smoothness, right? There's also smooth step. How many of you have used smooth step before? All right, about half. Smooth step is sort of smooth at the beginning and smooth at the end. So it has that really nice sort of apps on your iPhone feel. And instead of just a jerk and a linear motion and a stop, it's going to have a acceleration, and then it moves, and then it slows down to a stop. So it has a much nicer feel. And we can make that a simple version of it. We can make more extreme versions of it that start off even more gently and accelerate quickly to catch up. It's interesting, from that 2015 talk, we talked about smooth step 3 and smooth step 5. Those are 3rd order and 5th order equations. So if you dig around, you'll see some t cubes in the first one, and then the second one, you'll see t to the 5th power. There is no smooth step 4, which I think is interesting. We'll come back to that. A specific subset of nonlinear interpolation is what I call normalized nonlinear interpolation, or pure easing functions. So these are, instead of saying, well, I want to go from red to green, or I want to go from this position to this position, we're just isolating just the curvy part of the math by itself in a pure vacuum, right? So we're just saying, how are all the different interesting ways I can go from 0 to 1? I can go fast at first and then slow, or slow at first and then fast, etc. So if I take something from 0 to 1 over the course of 0 to 1, that's sort of a pure easing function or a normalized nonlinear interpolation. Just to give you an example of why I like this, and we'll give a couple examples. This is smooth start 3, the cubic ease-in, if you're going from start to end. You have to sort of range map it from where you want to go, and if you work through the math, you're actually sort of temporarily into a 0 to 1 space, and then you cube it, and then you have to range map back, right? Whereas that same function is just simply t cubed if you're working in the 0 to 1 space. So that's definitely the win. That leads to my principles of parametrics. First, it's almost always easier to modify t rather than the function that you're sticking it into, right? So that function may be complicated, and if you want it to go in reverse, it may or may not like that, or if you want it to do something funny, it may be complicated. But if you can write the function so that it just expects a t, you can just mess with t all you want and then pass that into the function. And then all those ways of messing with t are independent of those functions, and they're very easy to do, and they don't mess up the functions themselves. So to give an example of this, if I go back to this sort of parametric playground here, I've got all these different parametrics going, and some of them are more interesting than others. This is a Lissajous curve, some fractal sine waves that are added up on top of each other, some Perlin noise, wackadoodle, it's the technical term. Obviously, some of these functions are going to be hard to reverse or hard to modify, or maybe I don't even have the code to modify them. That's fine. This function is a combination of Perlin noise, cosine and sine, and some func. But if I just hit F11, now I'm going to make the parametrics for t go forward and backward for everybody. So now you can see everybody's going forward in time, backward in time, and forward in time, and backward in time. And I didn't have to write a single line of code in any of those functions, right, to do it, just because I'm messing with t itself. In fact, I can make it even more funky, right? If I look at this guy here, this is showing, now I'm using Perlin noise to affect the t itself, so it's just going to wander kind of back and forth. And that wandering effect is applied to everyone parametrically, right? It's going to sort of go up the helix and down the helix. It's going to curve through this, course through this noise. And whatever the heck this thing is doing, it's going to do it forward and backward seamlessly. And the second principle is life is better in 0 to 1, right? A lot of math disappears. So normalized nonlinear interpolation for the win. For me, I sort of view anything that I can turn into a 0 to 1 problem is like automatic victory for me because I spend so much time in that space, whether it's in a material shader or in some AI utility function or anything like that, because I just spend a lot of time. It's sort of like the more stuff we get to run on electricity, then we just reduce it to a single problem of producing clean electricity, right? So, all right, so let's talk about Bezier curves. So Bezier curves come in various orders. First order Bezier curves are called linear Bezier curves. They're not even curvy, it's just lerp. It's just so mathematicians can say there's a thing there. In fact, there's 0th order Bezier curve, which is a dot that's not moving. But it is interesting, knowing that they call this a linear Bezier curve, that actually gives us insights into some of the higher order curves. So it's just a lerp, so we're just saying, hey, there's some mix of A and B where T is how much B, meaning T is how far we got on this line, right? All right, so above that, much more interesting, are quadratic Bezier curves. And this is one pictured here. So here's a quadratic Bezier, and it generally has 3 control points. There's a beginning, a middle, and an end. And this beginning point and the end point, the line will always go to them. The curve will always go to them no matter where they are. But you'll notice that the middle point, unless it's just coincidence, the line actually never reaches it. So it's a guide point, we would say, or a control point, right? It's just influencing the curve. It's not on the curve. So that's the basic idea of a quadratic Bezier curve. There are a whole bunch of ways to interpret them. There are basis Bernstein functions that can be graphed and blah, 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 blah. I think it's much easier to think of this in terms of this algorithm, which is the de Castelnau algorithm, which is just lerping between linear curves. So effectively the way it works, and even if you know this will be nice for a review because we're going to go a little deeper with it. So conceptually, if I have this line on the left that goes from 0 to 1, and that's that little green dot moving across the line, and simultaneously this dot moves from 0 to 1 here, then I can draw a line between those, and that line is moving over the course of that period, right? And they're both on the same clock. They're both going t from 0 to 1 at the same time. And of course, then if we drag this out and sort of draw out the path that this takes, of course, this is all happening in real time, right? So we can do whatever we want. Then it actually tends to form a curve, right? And I know I sat in junior high when I wasn't making Dungeons and Dragons maps. I was drawing stuff like this on graph paper. So that actually, if we follow the course of a point across that curve, that is the actual curve created by the quadratic Bezier curve. And specifically, the way that works is that this, here, let me put this on mouse control, that this green dot is moving up here while this green dot is moving, and we said we have a line in between them. And then on that line, we're also going to move a point across that line with the same t. So right here, we're at 30%, so it's 30% for the greens, 30% for the blue, 40% for everybody, 50% for everybody. So that's the basis of the algorithm. Very, very simple, right? All right. And it's interesting that because we said a linear Bezier curve was just sort of a lerp from A to B, then if we want to, we can say a quadratic Bezier curve is a lerp of lerps. And somewhere in the math there's a t squared. And we can write it out as a polynomial, which again, the mathematicians would do. But this is my favorite way to think about curves, is the de Castelnau method. So that specifically is lerping the lerp. Does that make sense? All right, so again, you got 3 control points. You're moving on them, you draw a line between them, and then you draw a point on that line, all with the same t. That's the important part, right? And B is a guide point, but it doesn't actually affect, or the line doesn't ever actually reach it. So remember, this quadratic Bezier is actually very, very simple. You just lerp from A to B and B to C, and then you lerp between the lerps. And there you go. So it's just a lerp of lerps. So the math here looks pretty simple. If I call this point E, this right here, and this point F, then that's E is just going to be a blend from A to B, F is a blend from B to C, and then P, the final point, is just a blend of those, right? So if I write it in my compact form, that's it, right? Pretty fast, pretty simple. I don't have to know anything. I don't have to know about basis functions or polynomials or anything. Of course, I said there would be quadratic in there somewhere. That should be imply a t squared. Of course, since one of those is lerping the result of the other, I can plug in the equations for E and F into the other equations. So there is one equation that forms, and it's s squared a plus 2 stb plus t squared c, when you write it in my form, which is the s and t form. And there's our t squared. That's why we call it quadratic. Of course, why we call squared things quadratic, I'm sure there's a Latin reason. All right, so just to try this out, if t is 0, we plug it in, and sure enough, everything but a disappears. Meaning, at the beginning of the curve, it doesn't matter where the curve goes, you're always starting at a. And the math says so, right? And likewise, if I plug in t equals 1, then all those s's become 0, and they vanish away the a's and the b's, and it's just c. There's another interesting thing with quadratic Beziers, that they can also be controlled in I think, a much more friendly method. And this is what, for example, Visio uses when you're curve editing, and I'm sure a lot of programs. They can be controlled by what I call a mid-param method. So the idea is we pick and drag a halfway point that I wish was the point at t equals 0.5. And we'll walk through this here. There we go. So if I pick a point, and let's say this is the point I want to drag, I feel like this is much more convenient than picking some guide point that's sort of vaguely influencing the curve. So how would I do this? And by the way, this point is at the halfway point in time, or rather in t, right, in the parameter. So it may not be halfway in space, but it's definitely that the first half of the time is going to be spent getting here, and the second half will be equal on the other side. So how can we do this? Well, if we decide that we want this point to be where we're going to be controlling, we can then say, figure out the midpoint between A and C. That's right here, this green dot. So that's this. And then we find the displacement from the midpoint to the halfway point. In other words, I find this vector from here to here, from the green midpoint to this orange halfway point. And then whatever that is, I just go one more further from there, take that same displacement out, and that's where B should be. So this B corresponds to this control point. And so I don't really need any of that at all if I just want to control the midpoint itself. That's kind of a nice trick. Note, of course, that curves are not uniform, right? That sometimes the grid lines, if you will, are more densely packed than others, right? If I do something like this, I get a lot of grid lines up here, and then they're really stretched out far here. So the dot is also going to move, the point is going to move very quickly at first and then slow it later on. But that's also interesting. We can use it to our advantage. We could think of it as a velocity. We could think of it as a density. All right, so now let's get into why I wanted to give this talk. I want to talk about Bezier curves and how they relate to these easing functions that we have used, like ease in and ease out and smooth step. All right, so let's look at first quadratic Bezier curves versus easing functions. Then we'll get into cubic and Hermite and some other stuff. So in that 2015 talk, which is fine if you haven't seen it, the whole point of it was to show mathematically and geometrically how do you make custom easing functions. However, there's an even easier way with Bezier curves. So if I consider, and let me get some curves up on the screen. All right, so here I have a linear, a quadratic, and, which we'll talk about in a second, a cubic Bezier down here. And those are each going from 0 to 1 at the same time, so they're automatically synced, right? They can never get out of sync because they're just locked into that same t every time. All right, so I'm going to put them actually next to each other, sort of like this. It's just so we can make some interesting observations. And actually, I'll come back to this guy in a minute. So note that what's happening here is totally independent on x as it is from y as it is from z. So when we do these lerpings, if I lerp from some xyz to another xyz, we all know I just lerp the x and I lerp the y and I lerp the z. So actually this curve doing whatever it's doing, the x part is unaffected if I'm just playing with this in y, right? That ball, it might come down more, but it doesn't slow at all. It doesn't move any more or less to the right or left. And in fact, if I put that B, that mid-control point, right in the middle, then this ends up being the same as linear. That's kind of interesting. So we can easily produce some of these easing functions just by moving these points around now. Once we understand Bezier, and obviously it's incredibly simple, right? It's just a lerp of lerps. So for example, if I want a smooth start easing function or ease in quadratic, then I literally just have to put the B point on top of A. In other words, if I just go like this, voila, that is smooth start or ease in. And if I put the point here, then that's smooth stop or ease out. That's it. So smooth start is just a quadratic Bezier where you put the middle at the beginning, or you can put the middle at the end. Of course, if we're being nice and we're doing this in 0 to 1, then what that really means is we're going to go from 0 to 0 to 1, meaning we're going to go from 0 to 1 at the beginning and the end, and our influence point, our guide point, is also at 0, right? B is also at A. And likewise, the ease out function, since it's putting the midpoint at the right side, at the end, we're saying that on 0 to 1, I'm going to put the B point all the way over at 1, and that produces the ease out, or smooth stop. Of course, as I just showed, it's also easy to get it to act linearly. If I want it to be linear, then even though this doesn't look as nice algebraically as the other one, just basically put it in the middle is what that means. A plus C over 2 is the average of them. So if I put this in the middle, then this fancier quadratic Bezier curve now is masquerading as a simpler linear curve, right? Or lerp. And of course, if we're just doing this in 0 to 1, then put B in the middle is what we're saying. All right, so let's get into cubic. And we'll talk more at the end if there's time about why cubic is so much more useful than just quadratic. But it's very easy to do. Cubic Bezier curve is just a lerp of 2 quadratics. In the same way that a quadratic was a lerp of 2 linears. Of course, it says cubic, so there must be a t cubed around there somewhere. And here's the gist. We have 4 control points, A, B, C, and D, and we're going to do the exact same thing. So even if you don't know this, you can already predict it. We're going to lerp from A to B, from B to C, from C to D, all at the same time, all with the same t, and we're going to draw lines between them as they move, and we're going to lerp on those lines. And then guess what? We're going to lerp on the lines within the lines. And so this point P, that is the lerp of the lerp of the lerp, is the curve. It's going to map out the curve. And we can see that here. This is a cubic Bezier. So I have an A, B, C, and D. And the B and C points, again, they influence the curve. But other than coincidentally, the curve doesn't go over them. Right? But other than that, it's basically the same strategy that we were using for the other one. And you can get some much more interesting shapes with this, right? You can get loops that curve over each other, and you can get things that sort of hang out and then free fall. So it's a lot more powerful and flexible. And when we come into splines, that power will be even more clear. All right, so if a cubic Bezier is just a lerp of 2 quadratic Beziers, who themselves are lerps of 2 linears, that's just a lerp of lerps, right? So the math is E, F, and G are just lerps, then Q and R are lerps of those, and then P is a lerp of those. So that's the whole math, right? That's the whole function. And that's also stupid fast, right? Add and multiply, and a lot of it can be superscalar. And no rocket science either. So if we plug the bottom ones into the middle ones and then plug those monstrosities into the top one, we could get a super monstrosity function, right? And it looks something like this. S cubed A plus 3s squared tb plus 3st squared c plus t cubed. There's our t cubed. So that's why we know it's a cubic function. It has the power of 3. And if you remember, right, squared is a parabola, but cubed is like an S shape. And anytime you have something that's going to be sort of doing this back and forth, S-like thing, it must be at least as powerful as a third order to be able to do that. All right, so if we compare those equations written out, when they're written out, again, on Wikipedia, it's all in terms of t, so it's harder to see the patterns. But if you rewrite it like I like to do them with the s's and t's, I think it's much easier to see the patterns. So for example, if you look at just the numbers in front, 1, 1, 1, 2, 1, 1, 3, 3, 1. I can also look at the powers, like s is from the third, if you look at the bottom one, s to the third, s squared, s first, s to the 0 counting down, while the t powers count up, so it's just nicely symmetrical, as math tends to be. And then those number coefficients, if I make a pyramid, then that makes Pascal's triangle. Now do you recognize it? Right, and that's what that gobbledygook function at the beginning was doing. So you can see if I just add up the numbers, I get 1, 3, 3, 1, 1, 4, 6, 4, 1. And I can now, deducing those patterns, guess the equation correctly for fourth order quartic, fifth order quintic, however complicated I want my Béziers to be. So they can do funny things. All right, so now let's look at what kind of easing functions can we play with now that we have the more powerful cubic Bézier curves. So in that other talk, we talked about deriving smooth start 3 and smooth stop 3. If you remember from that first slide today, that's just sort of the more extreme version of smoothness, right? You're going to start out even slower and then come in at the end even faster to make up for it, right? So it's like this cubed version instead of the squared version of the curviness. Of course, there's a much easier way than doing all the algebra yourself. You can just play with Bézier curves. So if we now bring this guy into the party. So right away, we can make some guesses and some intuitions about what we might be able to do with these points. So we could see putting them both in the middle. Not sure what that does. If I put them at 1/3 and 2/3, it turns out then that masquerades as a linear, just like everything else. And in fact, it is always true for any Bézier curve or spline that you can always masquerade as if you were a wimpier version of the curve, right? Cubics can always pretend to be quadratics if they want. All right, so that's kind of interesting. Well, what can we do in terms of these easing functions? So smooth start 3 is the ease in cubic. That's if I have AAAC. So what I mean by that is if I take A, B, C, and D as my 4 points, if I take B and move it all the way to the beginning, and C and also move it all the way to the beginning, now I have smoother start or smooth start 3, or ease in cubic. For comparison, remember if I did that to the quadratic one, there's only one guide point to move, so that's smooth start 2. So now you can see they stay synchronized because T demands it. It's the same T going into all of them. They can't possibly get out of sync no matter how much I mangle them. But the B starts slower than the second one starts slower than the first one, and the third one starts even slower, which means it has to go even faster at the end in order to catch up because it's predestined to end on time because it's parametric. As you would imagine, we could do smooth stop, right? The cubic version of that. And that's, yes, just shove all the points on the other end. We'll just do that really quick. So this is smooth stop 2, or ease out quadratic. This is, if I push these points down here, smooth stop 3, or ease out cubic. Again, they start and stop at the same times, but the third one has to go really fast at first because he's going to take a long time sliding in to the home base at the end. Of course, if we're using normalized Béziers, we can just express those as 0 to 1 always on the end, the start and end. And then it's just where are we going to put those middle points. In the first case, we were putting them both at the beginning, which is 0. The second case, putting them both at the end, which is 1. All right, what other easing functions can we do? We did smooth step and hesitate in that other talk. And the way we derived them in the previous talk was if you lerp from a smooth start, which starts off nice, and then you sort of over time blend that into a smooth stop, and you do that blend over the course of travel, you actually will get a smooth step. I can show that visually. All right, so here are the smooth start functions. All compared. And you can see on the runway below that they always start and stop at the same time. Here are the smooth stops compared. And then here are some smooth steps. And you'll notice on the left I have a graph which is smooth start. But if I move my mouse, I'm going to make it so that it can be smooth stop. And if I put it halfway between them, it's a line. So if I want to make smooth step, the way I can do it is I have to be careful to time it right. At the beginning, I want to be this shape. At the end, I want to be that shape. So I'm going to go like this and sort of over time change it. And if I do it right, then the red will stick with the green. So mixing from one to the other can produce the same thing as the other function. And that's what we showed last time. We can also do something interesting, the hesitate function, which is start with a bang and then slow down near the middle and then accelerate again and go out with a bang. And that's really, really easy to do with this new Bezier formulation. Instead of putting, well, hold on, let me go back to smooth step. So we said we could have evolved smooth step by doing this crossfade, or we can just simply take the B point and move it to here, and the C point and move it to here. So now we have both starting smooth and ending smooth. That's smooth step. And I just derived it just by moving points around. And if I want to, I can actually write the algebra. It's very simple, and then plug in zeros and ones, which are great. It makes half of the math just vanish. If instead of doing that, I take this B and C guide points, and I swap them. So I'm going to intentionally sort of twist this up, and I'm going to put that one here and this one here. At precisely the ends, I get exactly the hesitate function, meaning it starts off strong, it comes to a complete stop for an instantaneous amount of time, and then accelerates again. Very smooth. So again, that's just cubic Bezier by manipulating various curves and the control points. All right, so here we have those formulations. And again, the smooth step is take the B and C and shove them to the outside, and the hesitate is to sort of crisscross them. And again, that looks really nice in normalized. And, whoops, I think I have a typo on that page. There we go. You didn't see that. There's some other interesting things we can do. Like said, we could make it look linear. That was no problem, right? If we just took this and put it a third of the way through and 2/3 of the way through. But we can do more than that. We can have a lot more fun than that. So for example, we can make it appear like it's linear, but we can also, as I claimed before, make it appear like it looks like a quadratic, as if it only had an A, B, and C. So how would we do that? So if I have my cubic with the 4 points, and I want it to masquerade as this thing that looks like the quadratic, I can actually place the points such that if B is 2/3 of the way on his leg and C is 1/3 of the way through, then it will look like the quadratic. And I can show you what I mean by that. If I take this down here, I'm going to make just a funky quadratic. And that's about as funky as a quadratic can get. Now I'm going to try to mimic that with the cubic. So if I place this 2/3 of the way along that edge, and this 2/3 of the way along this edge, then it will produce the exact mathematical version. So and that's true 4th order, 5th order, I can always sort of dumb down my Bezier curves, which is a very nice feature. For example, if I want to use that little midpoint grab a handle trick, I can use it on a cubic thing. I'll just make it feel like it's a quadratic thing, move the point around, decide where the B would be if it was a quadratic, and then figure out what do I have to do to pretend to be that quadratic. Sort of hand waving here. So anyway, any Bezier curve can masquerade as a lower order one. All right, so let's look at curve splitting. And this is really important that it's non-invasive curve splitting. And I've worked on several games where we're either authoring in 3D camera paths that are flying around, or the paths of objects that the camera is focusing on, or in 2D, just roads that people are going to come in and attack on, or that can travel throughout, or just that balls are rolling down these tracks. And when I'm making a level editor for that, or a tool or anything else, I want to have forks and joins, and I want the level designers to have as much specificity as they want, so I want them to be able to say, no, I need more control here. Let's chop that spline up, or that curve up, into multiple little curves. And when they chop it up, we want it to not suddenly change the shape of the curve. So that's non-invasive curve splitting. Because we're using this de Castelnau method, which is the lerp of lerps thing, there's a really nice miracle that comes out of this by accident, is that we can perfectly splice splines or curves into any two curves by using that. So here's how that works. So if this is a quadratic Bezier, and you can do this for cubic, quartic, any order of complexity. So if I pick some point, P, let's say right here, and then I want to identify what are going to be my ABC nodes of the first curve that I'm going to chop off. So P in this picture is like 70% of the way. So I'm going to make two curves out of this. One is the first 70%, and then the other curve handles the last 30%. So if I simply say this A, E, and P, and remember that the E was lerping from A to B, and then the P was lerping from there. So I'm like going down the chain of lerping, lerping, lerping. So if I go from A down the chain to E, down the chain to P, that actually produces a perfectly valid Bezier right there. So I can just cut that piece off, and it works just as if it hadn't been cut off. And then likewise, I can split the second half if I want. That will just be going up that lerping from P to F to C. So that right there is the second curve. All right. So I want to talk briefly about Hermite curves. I'll give a brief coverage of splines. I think we'll have enough time just to go into a little bit of it to give you a sense of why the cubic is so much more important than the quadratic, and just to give you a couple of tips to leave with. So the cubic Hermite curve is one that you've probably heard of, that people use a lot. That's even a little harder to understand, right? If I look at this formula, s squared times 1 plus 2t, t squared times 1 plus 2s. It's even worse if I don't have the st version. It's okay. Cubic Hermites are fine because they are exactly the same as Bezier curves. And I didn't know this for years. This is me helping past self. That if you have a Bezier curve, you can make a Hermite curve that's the same. If you have a Hermite, you can make a Bezier. In fact, in my engine, I just have a class that can act like it's Hermite or Bezier, however you want to touch it at any given moment. All right, so let me show an example of that. Okay, so in Bezier curves, we have start point, end point, and then these two sort of mysterious guide points, right? And they're not mysterious in the sense that we know exactly it's lerping from here to here and here to here, but they are a little bit mysterious in that, like, oh, that's not what I want it to do. How do I get it to do what I want it to do? Even though I know the math, it's still kind of cumbersome, right? Whereas a Hermite representation is the exact same math. It still has an A, B, C, and D. I just hid the B and C points, and instead I'm showing you the tangent, or I like to think of it as the velocity as it's coming into the curve, and then also the tangent or velocity as it's coming out of the curve. So now I can just say, thou shalt start here going up, and thou shalt end here also going up, and it says, fine, the only way to make that possible is if I go up, then down, then up, and the math just works. So Hermite splines and curves are much more intuitive for people to work with. And if I want it to sort of come to a stop, I can just make the velocity 0, and you can see the point comes to a nice little resting point at the end. And the good news is that you can freely convert, like I said, and it's very trivial to do. So if I say u and v are the velocities at those endpoints, like the velocity coming in is u, and then the velocity going out is v, then I can easily say, well, what would it be if it was an ABCD Bezier instead? I can get those, I can move them around, and I can say, okay, now that I've got that, let's switch back to the UV form. I want to play with the velocities some, right? So they're interchangeable. All right, so lastly, I'm going to go the full hour, I think. So we'll just try to keep this in another 8 minutes. Just looking a little bit at splines, and I want to at least let us walk away with a sense of why the curve types are important, how the Beziers feel different from a Hermite when we build them into splines, and how the quadratics feel different than the cubics. I'll show you what I mean. So a spline is just curves joined end to end. And I'm going to show one here. So this is a simple quadratic, but I could slap quadratics on the end, right? And now I have a quadratic spline. So it's just a chain of curves. That's it. One of the things that's interesting, and here I have a point that's going from 0 to 1, and then this point actually teleports back here. It's just that it so perfectly syncs up with this other point who then teleports back here that it looks like the points continue to travel, right? So that 0 to 1, 0 to 1, 0 to 1 makes its way all the way down the splines. And in fact, when we parameterize the spline, we could think of 0 to 1 for the whole thing, Or we can actually think of 0 to 1 to 2 to 3 for each of the segments, right? So for example, if I have a spline of 4 pieces, I could say that its t goes from 0 to 4. And now if I'm at t of 2.67, that means I'm 67% of the way through that third section, right, through section 2, starting at 0. So I could just find curve number 2 and plug in my 0.67 and ask it, okay, I'll ignore the other parts of the curve. How are you doing? So this would be like interpolating the spline and evaluating it. All right, so that's a quadratic spline. We have problems of continuity, and this is really where the big differences between the spline types start showing up. So let's start with the simplest spline type, which is this quadratic Bezier spline, right? And we go for this because that was the thing that we remembered from the talk, and it made sense, and it was just a lerp of lerps. I'm like, cool, I can code that right now. One of the problems with this spline is that everything is intertangled, and I can't really adjust it without breaking everything. So if I want this nice, smooth, continued motion, by the way, if I turn off the control points, you can't even really tell where one stops and the other starts, right? Because they're perfectly seamless. Well, now, if I want to make this angle of this thing change, well, now I've got this discontinuity, right? Where I have a sudden change in direction. So I could say, oh, no problem. I'll just swing this point around to fix it. There, now it's smooth. Except crap, now I broke this other one, so now I have to move him. Wait, hold on, I broke him. So now if I have 400 chain long, if I touch any one of those control points, I have to adjust all the control points. So that's not any sort of sense of local control, and the artist is going to be like throwing their hands up and crazy. So they look cool, they're useful, we can make them do things, but they don't give us any sort of power because our hands are bound. Anything we touch just breaks everything else. And by the way, the breakage is not just making it line up in a straight line. If I turn off the control points, I could do something like this. And you could say, oh yeah, that's a nice smooth curve. And it is, unless I'm actually walking along it. And then you can see now there's a sudden lurch that these guys go from slow to fast right around this corner here, because the lengths of these are not the same. So not only do I have to line them up like this, but I have to like make sure the lengths are the same on both. That's an impossible problem practically to solve. All right, let's try it again with cubic Bezier and see how it's different. So there's a cubic Bezier spline. And now I just have a hankering for changing this in the middle of the spline. So I can do whatever I want with this, and I'm going to put it over like that. And yes, I have to make this correction that this one has to be on the other side, and if I want it to be perfectly smooth, no sudden acceleration, then I want it to be mirror opposite, same length, same direction. And you'll notice I didn't break anything else because this point here affects this incoming slope or velocity or direction, and this one affects this one here. So I can tune these separately and easily modify any part of my curve without affecting the other one. So the reason we use cubic splines, cubic Bezier curves, cubic Hermite curves is not because cubed is cooler than squared or it's just like that much more mathy or powerful. It's because we can't work, right? Because the other thing doesn't have freedom of manipulation and this does. Hopefully that makes sense. Of course, because this is exactly 100% identical to Bezier, I could picture it with the velocities instead of the b's and c's, and it's just fine. And in this case, I've hooked it up so that the velocities, technically there are two different velocities at this point, right? There's one that's coming in, and then there's another one that's coming out. So if I had changed my code a little bit, I could have easily said, well, I could manipulate this arrow separately from the arrow coming out and intentionally create a discontinuity. But if I want something that's traveling or that's sort of seamless, maybe I want to have them welded together. And so this just is a nice, convenient way of saying, which way does it go at this point? Let's assume it's going that way, both coming in and coming out. I will say, if you're coding this, one of the things I recommend is that your data structures don't assume that the next point is that the next person's start is at your end. you might want a little teleport hop, right? And don't assume that the outgoing velocity is going to be the same as the incoming velocity. You may want a jerk, like a lurch. A case in point example of that from a real world game. Oops. Boom, 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 boom. So let's say I wanted to make a battle axe, and I have a curve editor thing. And so I want to make the battle axe so it looks like it's going to have some sharp edges and a nice round curvy edge. I'm probably not going to be able to do this fast enough. So I could have a strong starting edge followed by a edge that's going to come out like this, and then it's going to have a big sweeping blade, and then that blade is going to come up. And I don't have quite enough control points to do it. But I can't make those hard edges and stuff without having the discontinuities. So discontinuity is not necessarily a bad thing, and sometimes mathematicians will sort of get enamored with the idea of this is smoother than thou, right? But that's not always good. So having this in your data structures is helpful and useful. All right, we're almost out of time. So we can build splines out of just about anything. One other last thing, and I'll end on this. There are a bunch of types of splines you'll hear about. Now we know quadratic Bezier spline, cubic Bezier spline, cubic Hermite spline. There are Catmull-Rom splines, cardinal splines, KB splines. They're all the same thing, exactly all the same thing. There are a few that are slightly different. But Catmull-Rom, you look it up, it's going to be some complicated formula. Thanks, Wikipedia. It'll smell like, now what is this thing? It's just a cubic Hermite spline, which is just a cubic Bezier spline, which is just lerping, 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 right? So we know how to do it. So what the heck is a Catmull-Rom spline? So I don't think of it as a type of spline. I think of it as a strategy or an algorithm for making splines. So its main use is to curve through points. Sorry, I'm going to go 2 minutes over CAs. If I have points 0, 1, 2, 3, 4, 5, 6, I want a spline that goes through all those, and I want sort of the nicest spline possible that goes through them. I can use this strategy to do that. So I can say, hey, from 0 to 2, what direction is it going? Let's make that be the velocity in between. From 1 to 3, what direction is it going? Let's make that be the velocity at 2. And now I'm creating points with velocities, and those are Hermite curves, which I can then do a little algebra and get the Bezier curves, and I can draw them, and I know just how they work. So this is just a strategy for picking velocities. So basically, the velocity at any given point is just sort of the average of coming in and the average of coming out. So we are out of time, but that's everything I wanted to cover. So thank you guys very much. And we're in this room all day. We'll be back in 20 minutes. But if you have any questions, you're welcome to stay. Please use the mics if you want. Oh, just right there. Yeah. Just so we can capture it. Thank you. Appreciate it. Yeah, hi.
I just had one quick question.
Can you put the mic up? Yeah.
So first of all, awesome talk. I saw your one in 2015. It was super cool. If you have a cubic Bezier spline and you're trying to interpolate along it at a constant velocity, what strategy do you use to do that?
So yeah, I wanted to fit that in. There wasn't time, obviously.
Yeah.
There are a lot of ways you can do it, but frankly, I think the simplest way is to make a cubic or a linear Bezier spline, which is a fancy word of saying a line chain. Mm-hmm. So if you just simply, like the way I'm drawing it here, I'm not drawing a curve, right? There's no such thing on the video card. I'm just taking 100 little steps and then drawing the lines between them. And one of the things you can do is take a step and see, and then take another step and see how much did it deviate. Oh, wow, that's not a lot going on. I feel confident in these steps. Or you can just take a whole bunch of little steps. But if you build a simple linear list, then I just think of it as burning down the parametric. So I say, I want to move 0.6 along the thing. So I look at the first segment, and he's 0.1. I'm like, cool, now I have 0.5 left that I owe. And just sort of surf down it linearly. So in practice, that's what I do. There's other stuff you can do by deriving the polynomial and dividing by that and stuff, but I think this is simpler. And plus, you're going to have to do it for drawing anyway often. So.
Right. Okay, thank you.
Yeah. Yeah.
All the way down. First of all, thank you. Put a lot of order in my head because I've been building UI animation tools, and that really helps with what I'm building. I actually just wanted to ask, is there a way to get those sample little apps you've been using?
Yes, I will post the apps and the slides at mathforgameprogrammers.com, hopefully all of ours for the whole day. Some of the code is, like I actually lost the source code for this one, but I'll post what I have, and at least I'll post executables so you can play with them.
Awesome.
Yeah.
Thank you.
Yeah.
Maybe I just missed it while we were kind of blowing through some of the slides, but in the section about taking an existing curve and sort of splitting it into two subcurves.
Yeah.
I'm assuming, but I wanted to confirm if the t is then you have to get your original 1 to 0, figure out what where on that t you split it, and make that curve now its 1 to 0 is like that. You have to translate that percentage or no.
So I think it's easier to show here.
Yeah.
So if I have, whoops. So this is just a regular quadratic,
Right.
and I'll just do it live. So then if what is my hotkey? Yeah, so if I split it, I'm just going to take the leftmost point, the midpoint, and this right point, and so what was your question then?
Was then do you have to also calculate a new 0 to 1 t?
Yes. Oh, good question. So that's part of reparameterization, which I also would love to. Maybe I'll do a whole talk on that. Generally speaking, you can say this spline either goes from t is 0 to 1, but then the long part is going to take the same amount as the short part. Right. So actually, what you practice will do is just say the t goes from 0 to 0.7. And then the next one, t goes from 0 to 0.3. So each spline segment can know its parametric length.
Right.
And then that trickies a few other things, like when you go to the velocities model for the Hermite, then you have to sort of divide by what units, because you're in kilometers now and I'm in miles. Does that make sense?
Right, yeah.
But so other than our parametric density being different, that actually works great.
Okay, thank you.
Yeah. Yeah.
How would you measure the length of your curves? Because it's all 0 to 1, but the curve itself is actually longer than that, depending. So
Yeah, the simplest, brute force way is just traverse with 100 steps and just add up the length of the line segments. Okay. I'm sure there's probably an integral to do it I haven't bothered with.
Yeah, I looked into that a little bit a while back, and I couldn't find a way to do it in code.
Yeah, I think in one dimension you can do it rigorously, and I don't know, because the XYZ dimensions are independent, but then you have to sort of integrate across them all to get the actual crow's distance. So I would just chop it up and measure.
Okay.
Yeah.
Hey, that's what I'm doing, so.
Yeah, good. Ship it. And the good news is that's simple math that's super cache coherent. Your computer can do 100 of those, 10,000 of those, no problem.
Okay, yeah, my question was very similar along his lines. I was just trying to figure out how to get the arc length analytically of a cubic curve, because I know you can do it.
Get the arc length and what?
Of a cubic Bezier curve, because I've done it with a quadratic.
Yeah.
And find it analytically, but doing it with the cubic one, I tried to go through it and it was just getting hairier and hairier.
Yeah, that's what happened to me. I think the second time through on page 4 of the algebra, I'm like, screw it, I'm just going to cut it up like I do.
Yeah.
And the nice thing about cutting it up, kind of like a step and sample raycast, is it just absolutely works all the time if you're willing to do it.
Okay.
Yeah. Within.
I wasn't sure if I was the only one. So.
Let's do one more maybe. Yeah. Okay, we're done. Thank you guys. Be back here at 11:20 for our next talk.